With this video, I'd like to continue our discussion of Chapter 4.1, the development of a new atomic model. Let's review from the previous video. What do we mean by the wave-particle duality of electromagnetic radiation? Well, it means that electromagnetic radiation, light, and all other forms behave in two different ways. It behaves as a wave when it's traveling through space, but it also behaves as a particle when it's being absorbed or emitted by atoms. Remember in the previous section we saw Einstein showed that when an atom absorbs electromagnetic radiation in the form of a photon, it does so one particle at a time, and the amount of energy contained in that photon is called a quantum of energy, and we can calculate that amount of energy if we know the wavelength or frequency of electromagnetic radiation. So, why is this important? Here is an experiment you may have seen before. If I take white light, the light that comes off, for example, an incandescent light bulb, and I pass it through a prism that allows the light to diffract, I see a rainbow, which is also called a continuous spectrum. Okay? What that proves is that white light is made up of all of the wavelengths of light in the visible spectrum, Roy G. Biv, red through violet. Now, here's something strange. When energy is added to an atom of an element, the atom is excited to higher energy levels, but when the atom drops back down to a lower energy level, it emits electromagnetic radiation. But when we look at that electromagnetic radiation through a prism, things look very strange. And on the next slide, I'm going to describe to you what happens. When electric current is passed through a glass tube that contains hydrogen gas at a low pressure, the tube gives off blue light. It's actually pinkish purple. When this light is passed through a prism, 4 narrow bands of bright light are observed against a black background. Check this out. On the left is the gas discharge tube containing hydrogen. I excite the hydrogen atoms by passing electric current through it. When I pass that light through a prism, though, instead of seeing a continuous spectrum, that is, instead of seeing a rainbow of all colors, I only see what's called a line emission spectrum. Only certain wavelengths of light are observed, corresponding to bands of color. I see a red line, I see a blue-green line, I see a blue-violet line, and I see a violet line, and we can actually measure the wavelengths of those forms of electromagnetic radiation. Now, what does this mean? This proves something very important about the hydrogen atom and all other elements in the universe. Here's our conclusion. If only certain wavelengths of light are observed, then that means only certain energies are being emitted by the hydrogen atoms when they go from higher states to lower states. If only certain energies are being emitted, then only certain energy levels are possible in the hydrogen atom, which proves that the energy levels in the hydrogen atom are fixed, or as we say, quantized. Here's a simple diagram that shows fixed energy levels in the hydrogen atom. The arrow pointing from bottom to top represents potential energy from low to high. Think of it as a y-axis. Each of those horizontal lines refers to one of the quantized or fixed energy levels at which the hydrogen atom can possibly be. The hydrogen atom can only be at one of those particular energy levels. It cannot be in between. So if I were to represent a hydrogen atom going from a lower energy state to a higher energy state, I could draw an arrow pointing to there, meaning that the hydrogen atom can only exist at one of these states. It cannot stop in between. And if I allow the hydrogen atom to emit energy by dropping to a lower energy level, it can only stop at one of these fixed or quantized energy levels. Let me explain in more detail. If this were not true, if the hydrogen atom could be excited to any energy level and drop back down to any energy level, then all transitions would be possible, all possible energies would be emitted, and all possible wavelengths of electromagnetic radiation would be observed, which would be the continuous spectrum or the rainbow. But we don't see that. We only see certain lines corresponding to certain amounts of energies being given off, therefore only certain energies are possible. Here is a more detailed diagram that shows energy levels in the hydrogen atom and the corresponding transitions. Don't be frightened by this diagram. I know it's big and scary. Okay, each horizontal line represents one of the quantized or fixed energy levels in the hydrogen atom, which we indicate by giving them numbers n. n equals 1 is the ground state, n equals 2 is the first excited state, n equals 3 is the second excited state, and so forth. Each group of arrows pointing down represent a series of transitions from higher quantized energy levels to lower quantized energy levels. So for example, the Lyman series corresponds to all the transitions from higher quantized energy levels that end up in the ground state n equals 1. The Balmer series represents all the transitions from higher quantized energy levels that end up in the n equals 2 quantized energy level, or the first excited state. These energies happen to correspond to wavelengths within the visible region. 656.3, that's the red line. 486.1, that's the blue-violet line, and so forth. The other series, for example, the Lyman series and the Paschen series, are outside the visible region. We cannot see them with your naked eye, but they're there, and we can detect them by other means. Now, here are two very important questions. Number one, it's basically the same question asked two different ways. What can we conclude about the energy levels in the hydrogen atom from the fact that excited state hydrogen atoms give a line emission spectrum? We conclude that since only certain energies are emitted, only certain energy levels are possible, and these energy levels are fixed or quantized. Another way to ask the question is, what experimental evidence proves that energy levels in the hydrogen atom are quantized? The answer, the observation of the line emission spectrum of hydrogen proves that these energy levels are fixed or quantized. There is no other way to explain the fact that only certain wavelengths of light are given off, other than the fact that the energy levels have to be fixed. So, is there a physical model that explains quantization of energy levels? There is, and you're probably familiar with it. It's called the Bohr model. Niels Bohr was a Danish physicist in the late 19th, early 20th century who came up with both a qualitative and a quantitative model to explain quantization of energy levels in hydrogen. Bohr says the electron in the hydrogen atom is traveling around the nucleus in circular orbits. The energy of the electron increases with distance from the nucleus, that is, with the size of the orbit. The bigger the orbit, the higher the energy. The energy can only be in orbits of certain size which have fixed energy. Therefore, the energy is quantized. That's how Bohr explained quantized energy levels. The electron can only be in certain orbits which have fixed sizes and therefore energies. The electron cannot be between orbits. When the electron is in the smallest orbit, which corresponds to the lowest energy, the atom is in the ground state. When the atom gains energy by excitation, the electron is promoted to a higher energy orbit. When the atom returns to lower energy state, the electron drops down to a lower energy orbit, and the atom emits energy as a photon of electromagnetic radiation. And the energy emitted by the atom contained in that photon is equal to the energy difference between the initial and final orbits. Each line in the spectrum, the red, the blue, violet, and so forth, corresponds not to a particular orbit, but to a specific transition from a higher energy orbit to a lower energy orbit. And you've probably seen a diagram that looks something like this. The green dot represents the nucleus, the dashed circles represent the fixed orbits, n equals 1 is the ground state, n equals 2 is the first excited state, and so forth. This diagram represents the electron dropping from the third orbit to the second orbit. When it does so, it emits a photon of electromagnetic radiation that contains an energy equal to the difference between the higher state and the lower state. This transition actually corresponds to the red line we saw in the line emission spectrum. Now, what works about the Bohr model is he correctly predicted the wavelengths emitted in the hydrogen spectrum. Bohr won the first Nobel Prize in physics because he came up with a mathematical model that actually correctly predicted the wavelengths observed. What doesn't work is the qualitative interpretation, okay? And Bohr knew this, but he went ahead with his model anyway. What doesn't work is the fact that the electron cannot be circling the orbit like the moon orbits the Earth, because classical physics tells us that a charged particle moving in a circular pathway would constantly emit electromagnetic radiation, which we do not observe, so that can't be the case. The other limitation is that his quantitative model only worked for atoms that have one electron. It did not work once you added another electron. So we need a new atomic model, which we'll talk about in the next unit, which is the quantum mechanical model of the atom.